Hey guys, welcome back. In this video we are calculating the strain energy for a member with axial loading. So in the last video I introduced the concepts here. This is basically just what was left over from the last video. We introduced strain energy. Basically it's just the total work done by this load as it elongates the member. Another way that we can think about it is strain energy of a member is just an increase in energy due to the deformation. So graphically we can look at it, we can plot applied load up here and deflection here, and we just have to find the area underneath, and the way that we do that is integrating this expression. Alright, so the other thing that we looked at was strain energy density, and we basically came up with this expression here. What we want to do now is we want to apply some real numbers to this. So I grabbed an example from a previous video when we were talking about Hooke's law, and we have, let's just bring this all into sight. We had this rod with actual dimensions, and we actually applied this, we took this applied load, and we wanted to figure out what the deflection was, or the deformation was, sorry, of that member. In this video, what we want to do is we want to take the same example, but we want to figure out what the strain energy is in this member when we apply this load. So let's use our equations from the last video. We have our strain energy over volume is equal to our strain energy density. And the expression that we had was sigma x squared over 2e. Alright, so this holds true for elastic deformations. And basically this is the total strain energy, no sorry, this is the strain energy density. If we want strain energy, and then again in this case it's elastic strain energy, then we can take the integral over the volume. So we will go capital U here is equal to the integral of this expression. We have sigma x squared over 2e and just dv. And then what we can also say is that we know that sigma x is just equal to the applied load over the area. So we can rewrite this as the integral of p squared over 2a squared e dv. Now this expression is useful to us if we are dealing with members with non-uniform cross-sections. But if we have something like this with a uniform cross-section, then what we can do is we can rewrite dv, let me just write that a little nicer. dv is just the cross-sectional area times dx. So we can write this, let's write it over here. So we have our elastic strain energy. In the case where we have something like this with uniform cross-section, basically we can integrate that from 0 to L instead, and then we'll just substitute in this for dv. So we had p squared, and then we have a dx, and then on the bottom we had 2a squared e. Alright, we can cancel out one of those a's up top with one on the bottom, and then we can write this just as the elastic strain energy is equal to the integral from 0 to L of p squared over 2ae dx. Now all of this stuff is constant because it's just given to us in the problem, so we can bring that to the outside of the integral. So we have p squared over 2ae times that integral from 0 to L to 0 dx. And then clearly this just becomes, let's maybe write it down here. If we simplify that, we'll just get p squared L over 2ae. And this is the expression that we want to be using for members with uniform cross-section. This one was for members with non-uniform cross-section. So in the case of this problem, let's figure out what our elastic strain energy is. We have, oops, there we go. We have some things that we need, right? So we need, we have P, we have L, we have area. I think we already calculated that up here. Yeah, the cross-sectional area, and we also have E, 200 gigapascals. So let's fill that stuff all in. We can write elastic strain energy. P is 150 kilonewtons squared. 150 kilonewtons. I'm just going to write it out like, because it's squared, I'll just put 2 here, and this will just make it nicer for us to cancel out units. times L. What was L? Let's see. L was 500 millimeters, so that's 0.5 meters. Actually, no, we can leave it in 500 millimeters. 500 millimeters? Nah, let's do meters. Times 0.5 meters. Alright, so that's the top of the expression. Down here on the bottom we have a 2 times the cross-sectional area. Cross-sectional area we've already calculated here to be 314.16 millimeters squared. So let's drop that in, 314.16 millimeters squared. And times the last thing here, E modulus of elasticity, we have 200 gigapascals. Well, we can write gigapascals as kilonewtons per meter squared, if you remember that. Or sorry, kilonewtons per millimeter squared. That's the same thing as gigapascals. Alright, so now we can go and cross out some units. We have kilonewtons crossing out with kilonewtons, millimeters, getting rid of millimeters, and we'll be left with kilonewtons times meters, and that's in the correct units because for joules we're basically looking for some variation of meters times newtons. So if we go and simplify this, we'll just get the top will reduce to 11,250 kilonewton meters, and the bottom here is just unitless. It's just 125,664. So if you if you divide that, we're left with 0.0895 kilonewton meters. And that's an ugly number, so we're going to convert that into Newton meters. That is just 89.5 Newton meters, and Newton meters is joules, so we have 89.5 joules. That is our elastic strain energy that we've built up in this rod when we applied that load to it. So boom, there's our answer. The one thing I do want to say, actually, you know what? Let's throw a nice little green box around that. That's the elastic strain energy. The one thing I do want to say is we could kind of look at this the other way, or if we wanted to solve this graphically up here, this expression, basically we already talked about strain energy up here using this expression, and we came to this expression right here, 1/2 P1 x1. Well, in this case we know that if we call P1 150 kilonewtons and x1 1.19 millimeters, then we would have 1/2 times 150 kilonewtons. Or actually, let's just write this as 150,000 newtons times our x1, which was, I think that was what, 1.19 millimeters? Yeah, 1.19 millimeters. In meters, that is 0.00119 meters. And if you crunch that, you get 89.25 Newton meters. And 89.25 Newton meters, down here we had 89.5, so just a little bit of rounding there, but it's the same number. So just showing you that there's a few different ways you can kind of interpret this, or you can branch off at different points with the different methods here. But that just confirms that we have done this right, and we calculated the elastic strain energy to be correctly as about 89.5 joules.